Okay, let's continue. Today's course is still the advanced structure theories. And last time we talked about if we have the constraint equations. And the constraint equations are kind of the kinematic conditions. Let's go back to the example problems. Okay, if we neglect, remember the elongations is equal to the UB minus UA times sine theta plus BB minus BA times sine theta. Okay, so that's the elongation of any members. So we can always use the nodal displacement at both ends. UA and the VA, that's the displacement of the first nodal point. And the UB and the VB, that's the second nodal point. So we can always use the displacement components of the two endpoints to calculate the elongation of this element. Okay, so sometimes we like to make the simplified assumptions for something. If we neglect the axial deformations of the element 2 and the element 3, then we have the E2 equal to 0 and the E3 equal to 0. Okay, so that's the two constraint equations, or you can say they are the kinematic conditions. So then we can write them in a matrix form like this one. And the C, they are the coefficients matrix for these two kinematic conditions. And the U, they are the nodal displacement vector. At least you need to put in the related nodal displacements. If we like to formulate the E2 equal to 0, we need the nodal displacements of node 2 and the node 3. If we like to formulate the axial deformations of the member 3 equal to 0, then we need the nodal displacements for the node 3 and the node 4. Okay, so the U2, V2, U3, V3, and U4, V4, they are the four nodal displacements. They are related to formulate these two constraint equations. So at least you need 6 nodal displacement in this vector. However, if you like, you can use more nodal displacements, but those extra nodal displacements, they are not related to these two formulations, to these two formula. Since the other nodal displacement, they are not related to the two equations related to the elongations of these two elements. Okay, and then we need to do the Gauss-Jordan elimination method. Okay, then after we finish the Gauss-Jordan elimination method, we can make the partitioned part of the matrix. That's the first 4 element, the first 2 by 2 submatrix of the C matrix. We like to make them equal to the unit matrix. The unit matrix will be a 2 by 2 matrix. And remember, the unit matrix, which is a submatrix, or that's the partitioned submatrix of the original C matrix. And the remaining matrix, let's say that's the C bar matrix. Okay, if we use the 2 by 6 matrix, 6 by 1, 2 by 1, then the unit matrix will be a 2 by 2. And this one, the C bar matrix, will be a 2 by 4 matrix. And the U1, U2, since we need to do the full pivoting, when we do the Gauss-Jordan elimination method. So the U1, the sequence of the nodal displacement could be changed. Okay, since when you do the full pivoting, whenever you make the swap of two columns, you need to do the corresponding swap in the nodal displacement vectors. Okay, in order to keep the equations unchanged. So whenever you do the column change, also you need to do the swap of the nodal displacements. But if you did the row change, you don't need to change the sequence of the nodal displacements. Okay, so you need to know how to do the Gauss-Jordan elimination to get a matrix like this one. Then we can express the U1 is equal to negative C bar U2. Okay, so that's a procedure, and we will say the U1 nodal displacement, they are the dependent variables, and the U2, they are the independent variables. And then we need to express U equal to R, U bar. Okay, in these example problems, since we got two constraint equations, therefore the dependent variables, the number of the dependent variables will be equal to 2. And if we express the complete global displacement vectors, usually if we got the 5 nodal points, the global displacement vector will include 15 variables. Okay, you have the U1, V1, the theta 1 for the nodal 1 until the last, the U5, V5, and the theta 5. So the complete global displacement vector includes totally 15 variables. Two in these 15 variables, in this derivation, the two dependent variables, they are part of the U vector. And two in these variables, they can be expressed as functions of the other independent variables. Okay, so if you replace these equations to express the two dependent variables in the U vector, and the other 13 variables, they will be shown either in the U and the U bar. So the other variables, they are the independent variables. Okay, so for the independent variables, you just say, for example, the U1 equal to U1, V1 equal to V1. So you need a coefficient 1 in the R matrix, and all other coefficients equal to zeros. Okay, so then you need to get the R matrix. For these example problems, it will be a 15 by 13. The U vector is 15 by 1. The U bar vector is 13 by 1. Okay, so that's the result we got from the previous lectures. Okay, after you finish this, so remember we can assemble the global stiffness matrix. Okay, that's the global stiffness matrix. And remember the U is equal to R times U bar. The U is equal to R times U bar. And the P times, and also the if we like to calculate the strain energy, which is the work done by the, okay, so that's the, and if we replace this one, so it will be the K R and if we multiply the R transpose, if we multiply the R transpose to both sides, you will get the this one. And sometimes we will call this one, which is a condensed matrix. Okay, in the previous example problems, the original K matrix, which is a 15 by 15, and the condensed matrix will be a 13 by 13 matrix. So that's why we say it is condensed, since the dimension of the global stiffness matrix, which is originally we got a 15 by 15 matrix. After the condensation of the stiffness matrix, we got a 13 by 13 global stiffness matrix. And all this procedure start from you formulate the two elongations of the M members equal to zeros, and you need to formulate the C matrix. You need to calculate. You need to do the Gauss-Jordan eliminations. You need to get the R matrix, and then you need to calculate the R transpose KR. Okay, to get the reduced. Kinematic condensation. Okay, since we got a condensed matrix based on the kinematic conditions, for these example problems, the kinematic conditions come from the two elongations, the two elements, we assume their axial deformation can be neglected. So we have the elongations of these two elements should be equal to zeros. Okay. Based on these two kinematic conditions, we can get a condensed matrix. Okay. So that's the another type of the kinematic condensation problems. The first examples, if we negate the horizontal beam element, then the solution procedure for the kinematic condensation will be relatively easier to do, since we need to do only the add columns to the columns, add rows to the row. Then we can get the condensed matrix. Then we can get the condensed matrix. However, if we got the inclined elements, and also we need to neglect the axial deformations. Then you need to finish all these procedure to get the condensed matrix. Okay, I will take a break here and continue in the next lecture.